everyone, and welcome back to the Towards Data Science podcast. So today we live in the era of AI scaling, where it seems like everywhere you look, people are pushing to make large language models even larger or more multimodal, and they're leveraging ungodly amounts of processing power to do it. But although that's one of the defining trends of the modern age of AI, it's not the only one. Because at the far opposite extreme from the world of hyperscale transformers and giant dense nets is the fast evolving world of TinyML, where the goal is to pack AI systems onto edge devices. Now, my guest today is Matt Stewart, a deep learning and TinyML researcher at Harvard University, where he collaborates with the world's leading IoT and TinyML experts on projects that are aimed at getting small devices to do big things with AI. And recently, along with his colleagues, Matt co-authored a paper that introduced a new way of thinking about sensing. Now, the idea here is to tightly integrate machine learning and sensing on one device. So, for example, today we might have a sensor like a camera embedded on an edge device, and that camera would have to send data about all the pixels in its field of view back to a central server that might take that data and use it to perform a task like facial recognition. But that's not great because it involves sending potentially sensitive data, in this case images of people's faces, from an edge device to a server, which introduces security risks. And so instead, what if the camera's output was processed on the edge device itself, so that all that had to be sent to the server was much less sensitive information, like whether or not a given face was actually detected? Now, these systems, where edge devices harness onboard AI and share only processed outputs with the rest of the world, they're what Matt and his colleagues are calling ML sensors. Now, ML sensors really do seem like they'll be an important part of the future, and they introduce a whole host of challenging ethical, privacy, and operational questions that I'll be discussing with Matt on this episode of the Towards Data Science podcast. You are the first person who's done the hat trick on the Towards Data Science podcast. So first off, congratulations. I think we'll have a trophy made out for you, and you can hang it on your wall, or, well, I guess not hang it on your wall. Anyway, we'll make the trophy so you can hang it on your wall. Great. Well, I think this conversation is, by the way, going to be really interesting. Anybody who hasn't heard Matt's previous episodes on the podcast, I do recommend checking them out, especially the last one, I think it was. We talked about TinyML, this idea of building edge devices with machine learning on them. That's sort of Matt's specialty. So today, Matt, we're going to be diving into some of your more recent work on kind of a new kind of sensing strategy paradigm for the world of modern day AI that I think it's going to get a lot of attention here. This is something that I'm personally really excited about as well. Before we get to that, though, maybe a bit of a primer for people who are not as familiar with the world of TinyML, of edge machine learning. Can you speak a little bit to, like, what's this landscape? Like, what are some of the special challenges that come up when you're doing machine learning on edge devices, and what does the state of the art look like in this space?
Yeah, sure. So maybe I should first give some context on sort of how this became a field in the first place. And so most people are familiar with sort of the growing model landscape. So you have these large language models, which take weeks to train and use hundreds of GPUs, and they have the carbon emissions of like a small country or something like that. And there's really sort of this bifurcation that happened where people were like, okay, well, we have these huge models, but there's also stuff we could do at the small scale as well. And this kind of lent into the sort of IoT landscape. So if you think of IoT, you're thinking of cloud connected devices. And so the cloud is fundamentally that sort of big ML space where all of the computation happens. We call it sort of compute centric. So we're sending our data up there, and that's where all the fun stuff's going on, and then they just send the results back. And so if you imagine something like Alexa or OK Google, you're talking to it, and it's going to send this information up to the cloud, and it's going to do its fun stuff and send it back. So it's fundamentally like a dumb device. It can't actually do anything itself. The only thing it can do is listen for you to say that word. And that in itself is an application of tiny machine learning. So it's listening out for that specific word for you to say. In sort of every 1 second, it's going through intervals and saying, did you say OK Google? Did you say OK Google? and most of the time you don't. And funnily enough, if you do say it, but it's not sure if you said it, it's going to sort of prime itself to be like, okay, now I'm really listening out to hear if you're saying that word. But yeah, one of the main issues with IoT is, you have to be connected to the cloud. So it consumes a lot of power because you have to power the antenna. And, this sort of gets into the weeds a bit, but generally communication is quite an expensive thing to do energy wise. So, and also, people can extract that information if they are listening in on it. So there's also sort of a security loss. And they're sending that data to the cloud, and you have no idea where it's going or who has access to it or what other stuff it's being used for. So really, there's sort of some privacy, security, transparency concerns going on there. The nice thing about TinyML is you don't actually have to be connected to the internet or to the cloud because the intelligence is embedded on the system itself. So you have a neural network that's on your device, and your device is, doesn't have to be connected to the cloud. It's precludes the possibility of someone intercepting that information, stealing your data, or having the data stored on the cloud in the first place. And so there's a lot more stuff you could do with it. You can put it on machines and do preventative maintenance by listening out for when is the machine starting to sound clunky? So maybe I should go and check on it instead of waiting for it to break. Or it's in iPhones. It looks to see if you're trying to talk to Siri or something like that. I hope I don't activate my phone. But yeah, so that's kind of the primer for TinyML in itself. But there's still some sort of privacy and transparency concerns because you don't know what that network was trained on that's on this device. You don't know. Sometimes if it is connected to the cloud, you don't know what it is doing. Maybe it's just doing it for firmware updates, but the point is you don't really know. And so that presents some additional concerns. And, this kind of did come to a head at one point when the Google Nest thermometer, I don't know if anyone's heard of this, but basically they found microphones inside these thermometers, and people were like, well, what the hell is this for? Like, it's a thermometer. Why does it need a microphone? And it turns out it was actually being used to listen for smoke alarms, things like that. But obviously, if you have a microphone in there, they could obviously use it to extract other information. So really, the transparency angle is something that, as we start to get more and more cameras in our devices, it's going to become a really big factor for people. And, we even had a professor who works in embedded systems, and he bought a TV recently, and he didn't even know there was a camera in it. So that kind of shocked him when he worked it out after about 6 weeks. And, if someone as learned as that, who works in this field, doesn't know that there's a camera in his TV, then what hope do the rest of us have?
Absolutely. And it speaks to this, obviously privacy, security, all that, but also just consumer trust. I mean, to your point, you discover one microphone, one camera in one of these devices that doesn't seem like it should have one. And this is there's a major risk to the whole industry, really, as people start to wonder about this stuff. Now, I think it's fair to say that you've done a great job giving a sense of the stakes here. This seems like a very important problem, and one that maybe a lot of people haven't thought of through the security privacy lens. But what about the headache? So the headache of putting machine learning on an edge device, presumably there are a whole host of different challenges that come up in that context. Can you provide a little bit of an overview? What's the bane of your existence as a person who worries about things like TinyML?
Yeah, so I mean, there's a few, and I would say one of the main ones is the heterogeneity of the computing platforms. So that is to say, there's lots of different systems that you have to work with because these companies build their own circuit boards and sensor systems, and really for tiny machine learning to be successful, it has to be able to interface and be deployed on each of these individual systems. And there's entire companies and infrastructures now that their sole function is to do this one thing. So that's kind of a problem that people are already sort of on task to solving. And there's very clever ways of dealing with that. And then there's kind of the social problem of, like we discussed, how do you best communicate with all of these stakeholders, like the companies, make it easy for them to build these devices, with the end users to make sure that they themselves, aren't scared by having a camera take pictures of them because they don't know what it's going to do with it, or listening to them 24/7. And then there's actually putting it on the device itself, like making sure that the device has enough memory to fit the network on, making sure you have the right sensors. And then also, one thing that's becoming more common now is people want to start training on the device. And that's pretty difficult because in order to train a neural network, you have to have gradients. And as people probably know, if they're familiar with machine learning, like you can't really get, like you need very small numbers to train this network. And generally these systems are like 8-bit or something. So you really don't have the capacity to sort of manipulate small numbers and float variables, just because, you're working with an 8-bit microcontroller, it doesn't have that capacity. So it really has to be done off the device. And so there's clever ways around this. So that one of them is called federated learning. So it's where you extract all the information from, say every person's iPhone, all of their data gets sent up to the cloud, and it kind of gets compiled into this huge data set, which then is used to train a model, which then gets pushed out to everybody else. So it's kind of like your individual information is being used to train a large scale model, which is then condensed and sort of re-uploaded. But obviously you have to be cloud connected for that to be a possibility.
Right. Okay, so that's really helpful, and I think gives people a bit of a sense for like the challenge of this space. There are so many kind of things that almost intrinsically, this industry is one that likes big models. It likes consolidation, and as a result, a bit of a bias in that direction. Whereas this edge device stuff, which is really important, still has a lot of those kinks to be ironed out. And so we're about to jump into this conversation's exploration of this new paradigm that you've proposed along with your colleagues, this idea of ML sensors, kind of a new way of thinking about what it means for a sensor to do its work in the age of AI. So I wonder, for people who are less familiar with the idea of sensing, with the idea of on-device sensing, could you explain what's the current on-device sensing paradigm? How is it currently tackled? And then how is that different from what you're doing with ML sensors today?
Yeah, so right now, the way that tiny machine learning works when it's deployed is you have sort of a model that's embedded on this microcontroller in some flash memory, and there might be a few sensors on board. So there might be a camera, and the camera is a peripheral of the device. So that is to say that it's like fully connected to the system. And so that data is then being sent to the RAM, which is, being used to interface with the processor. So it's all on the one system. So if someone has access to that system, they have access to the raw data itself. And, they can manipulate and do whatever they want. The crux of the thing that we have proposed, the ML sensor, it's not actually, a defined piece of hardware or architecture. It's more of a logical framework that we've proposed. And so what really the crux of it is a separation of the computation from where the raw data is to where the processing occurs. And so that's probably going to sound a bit confusing to people that aren't familiar with this kind of thing. And so maybe a good way of thinking about it is passwords. So for example, if you there is a law in the US called PCI DSS, which says that if someone hacks into, it says that you can't store passwords in plain text, basically. So on a database. So if someone hacks into the database and they get this, list of all these passwords, they're not actually the passwords. They don't have the information already. They have a hash of the password, but this hash you can't reverse it, and so you can't extract the actual password from this hash. And so even though the information has been stolen, actually the user is still kind of safe. You have to do a lot more stuff in order to extract that information. And it's kind of analogous here. If someone hacks into the system, they could feasibly get the raw data, but it's just so much more difficult that it's almost a waste of time. And you'd have to be physically present to extract it from the hardware.
So does this imply like a tight coupling then between the machine learning and the raw data collection? Like they're so integrated that it's kind of hard to think of the raw data in the absence of the analysis, the machine learning on top of it?
Yeah, so the current way right now is there is the machine learning and the processing, they're coupled together. So they're occurring on the same device in the same memory. Whereas what we would prefer is that there is this sort of separation of computation. So in traditional memory architectures, you have a concept of user space and kernel space. And basically all that means, to those who aren't familiar, is that the user shouldn't be able to interact with this kernel space, because the user is, the user, and they should be able to do the things that they want to do, but they shouldn't be able to effectuate this sort of crux of the system, the operating system itself. And so there has to be this logical separation of memory.
Like just so you don't accidentally do something stupid, for example.
Yeah, so you don't delete, important
your
files.
Operating system, right? Yeah.
So yeah, and this, we've kind of taken that and sort of applied it to this computation system instead. We've said, okay, well, what if we had a sensor here which had some sort of processing power on it that was interacting with the raw data itself, and then it sends information to the actual processor, which then performs, additional functions. And so this ML sensor is a self-contained modular system. You could imagine it like a circuit board or a little sensor that you go and buy from a shop. But the point is, it's embedded on that device, and you don't need per se to be connected in this logical way to the actual main processor.
Can you give like a concrete example of like how the data might flow in, say, a real system?
Yeah, sure. So right now we're trying to make an open source version of a person detector. And so, the application of a person detector is there a person in this picture, yes or no? And if it's yes, it would send a binary response that would be like a 1. And if it's a no, it would be a binary response that's a 0. And so an ML sensor in this case all it would have is a power signal and a ground signal and the data output signal. You don't even need a data input signal because the sensor is already on the device. And so on this sensor, you would have a camera, and you would have some kind of processing capability, perhaps. And basically, it would perform the computation at the level of the sensor. So this is a truly data-centric device. And it's sending the high-level information, which in this case is the 1 or the 0 that says, is a person present or not? And it's sending that information to the broader device, the processor. And so, that processor doesn't know what you look like because it doesn't have access to the picture, the image. It only knows that there's either a person there or there isn't. And
right.
So if someone hacks in, they don't have the picture of you. They can't take that information, upload to the cloud, work out how many people live in your house, what their ethnicities are, what your habits are. And there's so many things that you could do with this information that would make people uneasy. And this is kind of a way of giving them the transparency and the assurance that that isn't happening, because this device only has one capability, and that one capability is to tell if there's a person or not in the picture.
So it's essentially, it's almost like we're moving from this age of thinking of sensors as things like cameras that give us a bunch of raw data about the environment, to sensors as like there's things that have some kind of onboard intelligence that do some of the chewing, the number crunching for us ahead of time. And then the sensor, what we get out of it is this like distilled thing, this conclusion already for us to chew on later. So essentially, as you say, like we're not sending all these pixels. We're not sending, Matt Stewart's face across the internet. We're just sending, like Matt is here or Matt is not here. And that's the signal that's getting shared to the cloud or shared elsewhere. That's kind of the idea.
Yeah, pretty much, because inevitably some of these devices are going to have to be connected to the cloud. But as long as there's some assurance that what data is being transferred, and that it's not sensitive information, then I think people would probably be okay with that. Yeah. I mean, there is still concerns of what level of information is correct. This is maybe a very simple example, the person detector, whereas with things like voice data or other information, it maybe becomes a bit less obvious what the correct way is. So there obviously has to be some sort of, people have to just have a dialogue about this and say, what's the appropriate mechanism for each application? And so we're not really sure at this point. This is more of like a philosophy paper and
Yeah.
discussion. Yeah, so I know we were discussing before about operating systems before we started the call, where you have this sort of time in the 80s and 90s where everybody was releasing these sort of philosophical papers of saying, what's the role of operating systems in the modern day for humans? What should it be able to do? What should it not be able to do? And now when we look at things like this user and kernel space, it's just so obvious, like, oh, well, of course you wouldn't want the user to be able to delete the file system. But back in those times, it wasn't so obvious because no one had done it yet. And the same thing's kind of happening now. We're saying, what is the role of sensors in this world where we now have machine learning? And in some sense, it's a much more complex problem because, there's a lot of things you can do with an operating system, but there's also a lot of things you can do with machine learning. It's, like the fifth pillar of science, essentially.
It really has you think about, as you say, like, what is a sensor? What does it mean to sense something? And thinking about how to cleave reality at its joints in a way. Like, there's so many different ways you could think about segmenting, like, this part is the sensor, this part is the processing or whatever. And this, it also ties into, like, the product strategy, right? So if you imagine being a company that, like, builds ML sensors, I imagine one question you'd have to grapple with is, like, what's the level of customizability, for example, of the onboard AI? So for example, we take a camera and we can turn it into an ML sensor that does face detection by having an algorithm that does facial recognition on board. Or we could tweak that algorithm to make it do, I don't know, age prediction or something with a little bit of fine tuning. So if you give the end user some access, some ability to tweak through transfer learning or other means, the onboard AI, I guess that feels like it might start to flirt with making it less of an ML. I guess it's still an ML sensor because you still have the sensing on board. But do you have any thoughts about that? Like, from almost a production standpoint, do we get into like a vast permutation of like a kind of ill-defined sensor devices?
Yeah, I mean, there are a lot of questions about that, and we don't really know because right now no one's even built an ML sensor. Some people think they have just because maybe it's not the clearest definition that's been created, but yeah, there's certainly a lot of things you can do with it, and we're not quite sure what the role is yet of what this is going to be. But we do know that this is probably sort of the right direction to be going in, because this is sort of a privacy by design, security by design, and if we do it correctly, transparency by design approach. And so one thing we've actually said is, if you build these sensors, the ones that are most commonly used, they should probably be open source. So that's why we're trying to make this open source person detector, because you could imagine, every house in the future has their lighting system controlled by a person detector, because you don't need a light on in a room if you're not in the room. And that would be a simple way to sort of reduce energy costs in a very obvious way. And you could do the same with, maybe your heating system turns on when you're in the house and it turns off when you leave. You don't actually have to physically do it yourself because sometimes you're going to forget. And so there's sort of those applications of it. But you could imagine that there's a lot more you can do, and it gets very complicated when you start doing things like age prediction, and then it becomes more like a traditional big ML system, and you would have to have sort of 10 sensors coupled together. Honestly, I'm not really sure. That we have proposed the idea of composability, which is, if you had this person detector, you could theoretically link it to another device which does face recognition, and you could use that for, say, letting people into their house, like a smart front door lock, I suppose.
Right.
But again, we're not exactly sure how that would work functionally, but it seems like it would be, it's plausible. And if you can do that with a privacy by design approach, where you're not, having to get tens of millions of people's faces uploaded to the cloud, I think people would prefer that generally.
Yeah. No, that seems like a really big plus to this. One aspect that seems really interesting in this context too, you talked about this idea of data sheets in your blog post and paper. So just like by way of background, I guess, for everybody who's listening, the data sheets are things that usually apply to traditional sensors, and I'm sure Matt will correct me if I'm wrong. They basically give out basically performance specs for the sensor. Here's what it can do well, here's what it can't do, and so on. And then there's this question of like, how do you apply data sheets to ML sensors when there's some interesting data processing happening on the device, and what do those data sheets look like? Can you speak to that a little bit? Like, how do you think about the data sheet ecosystem in this context?
Yeah, so I mean, I could definitely go in a rabbit hole here. I would say, I mean, I've worked a lot with sensors, so I've read a lot of these data sheets, and I'm kind of familiar with what they contain. But there's also a famous paper called Data Sheets for Datasets, and this kind of takes the idea of the sensor data sheet and starts applying it to data in general. And then I saw a paper called the data nutrition label, and that starts, trying to condense all of this information into sort of a smart label that is something you could communicate to a user. So you can imagine if you're buying a TV and you see a symbol that says, "Hey, this has a camera on it," that would
Right.
be like a really useful piece of information, potentially, because you might not be okay with that, or you might be flattered by the transparency of the manufacturer and say, okay, they don't just want to steal my information, they want to tell me, or maybe you just be like, I don't need that functionality.
Yeah.
And so in the data sheet, we were like, okay, well, how do we make this information sort of in a condensed place where we're adding this electrical characteristics that you get in a normal sensor with the machine learning model and the data set characteristics that you get in this sort of idea of data sheets for data sets, and then also combine that with what should the end user care about. And so we came out with this idea of, okay, maybe each ML sensor should have this data sheet. But then obviously you get into the issue of, okay, well, I could just lie about everything. I could say this doesn't have a camera in it, whatever, like no one cares, no one's going
Yeah.
to read this. And so then we said, well, maybe there needs to be some kind of regulation behind this, especially as you're really going to start seeing in the next 10 years, like cameras everywhere in your house. It's already kind of happening with this like smart mirrors I've seen like smart workout things, which have, like a bunch of cameras on, they're looking at your poses and seeing if you're doing your like downward dog in yoga correctly. um, and so as these become more and more common, I think people are going to start to have a bit more resistance. And so they would really like to have this sort of information. And, people haven't really started thinking about this right now. And so you could imagine we could very easily get to a stage where it just suddenly is a massive problem and no one's thought
Yeah.
about it. And it would be a much better position to say, okay, we've already thought about this and we have this procedure in place, and maybe some mechanism in place as well for people to have some assurance. And so, there could be a third party entity which does audits in the same way that you might audit an algorithm for bias, or you might audit a company to make sure they're not, cooking their books or something like that. And that would give assurance to these people that, okay, this sensor only has this functionality and it's been verified by somebody else, so the manufacturer isn't lying, and I know this data is safe and secure and protected. And I think that's kind of probably the best we can do, but it's hard to say at this point.
One thing I'd imagine might be a challenge here too is like the combinatoric explosion of possibilities, just with like every possible combination of algorithms and hardware. And then you'd have to presumably kind of measure their properties on a data sheet like this. So how would you avoid like having to test almost like every sensor variety for robustness and performance characteristics before it's shipped? Is that sensible?
There's something called MLPerf, at least, which is sort of a benchmarking framework. And the group I work with, they created or helped create a benchmark called TinyML which basically is the same idea. So you take a bunch of standardized data sets and you say, make this very specific model and we'll look at the performance of it. And it can assess hardware performance in terms of hardware characteristics, the number of inferences per second, or like energy consumption per inference, that kind of thing. And so there's ways of benchmarking individual systems for the same task. In terms of like a manufacturer that's selling their sensor, ensuring that every single one is correct, that gets into sort of more of an engineering and quality assurance problem, I guess. And so you could test a batch of them every so many sensors or something, and you could send those to an auditor, or you might just have a suite in the same way that you do a unit test on a software library. You might have a way of doing a unit test on one of these sensors and just make sure the accuracy is within, a certain bound or something like that. So I think it's definitely a feasible way to do it. Again, if this is the best way or a suitable way, I'm not sure, because again, this is a very new field and I'm
Yeah.
just one person. I'm sure if you made an FDA for algorithms, they might have much more nuanced views than myself.
I was kind of more thinking, what happens if, if it's the case that a manufacturer says, hey, the end user can specify an algorithm that they want to slap onto this thing. Then the manufacturer might get into the business of pumping out a whole bunch of different combinations of these things, and perhaps more than they could test at scale. But well, I mean, I think to your point, it's an engineering challenge more than anything. One thing
Oh,
this
so wait,
does.
sorry. So do you mean like they could have one with like 100 different networks on that they're selling at the same time?
Yeah, exactly. Yeah, like I'm imagining, a matrix of, hey, like, do you want to, like, facial detector, age detector, whatever, and that's just for when you have a camera on board. Then you change the hardware, and it's like now we have a whole bunch of other. So, especially if, as I imagine things continue, you could imagine customers actually installing their own custom software on these things. In which case, kind of assessing the performance characteristics of these things maybe the responsibility would then be delegated to the actual customer at that point, because they're the ones with all the requests. But anyway, so many directions that this thing could go. It's hard to pin it down.
That's pretty fascinating, actually. Yeah. I know one thing we were talking about a lot was, we've mentioned the model performance and the data sets, but I'd say that probably the most important section of the data set that I kind of didn't really discuss is the end-to-end performance. So if you have a person detector, you might want to know, okay, well, how does the accuracy depend on how far I am from the sensor? Because maybe I'm going to put it on a
Right.
building and it's going to be looking 100 meters away, and maybe it's going to be mostly operating at nighttime. How does the sensor get affected by, changes like that? And so that would be the important section for those people. And yeah, you could imagine certainly like a manufacturer having 100 different person detectors, but they're probably going to pay for that in the sense of no one's going to know what to buy.
Yeah.
Some what's it called, the illusion of choice or something. You have too many options.
Yeah, the embarrassment of riches in a way. I guess the yeah, it all depends so much as well on like kind of the business model too. Like, we just talked about this idea of like, is it the company that's installing a bunch of pre-developed algorithms that they themselves can assure, or is maybe it's a kind of developer tool, if you will, a platform where other companies can order things, install their own algorithms, and then or who knows, even their own hardware. I have no idea. This is the future. I have no idea how where this is going to go. But it kind of shows, I think, the fact that you've identified this kind of this division, this natural separation between the sensor and kind of on-device sensing and the rest of the world. The moment that it kind of clicks, it really clicks, and it's like, okay, this is going to become a thing, and we do have to worry about what goes on that sensor, the dynamics of like who's responsible for what components of it, how do we assure performance and that sort of thing. And then one thing that comes to mind in that context too is like adversarial attacks as well. Like, do you have any sense of how adversarial AI obviously is done today to people find ways of defeating or deceiving AI systems, big scale AI systems, facial recognition, that sort of thing. Do you think that that's going to change at all in the context of ML sensors? Does that introduce any new dimensions that are relevant for adversarial attacks?
If I'm totally honest, I haven't thought about that too much. It certainly would be a problem. I mean, because adversarial attacks you can't really avoid against too much unless you do sort of smoothing characteristics within the model landscape itself. Make sure that someone can't just like put a certain mask on and pretend to be Jeremy or something like that and fool this facial recognition software. But yeah, that would be certainly something that when people are designing the ethical implications, or maybe in the data set themselves, they could even test. Maybe there
Right.
needs to be some kind of uh, challenge that someone creates where they're like, okay, we're going to test all of these different algorithms or models or sensors, and we're going to see how well they perform when we're trying to, screw with them. And that could even be a section of the data sheet. Who knows? I mean, the one we proposed is just an example of a data sheet, but that's not to say that should be the final, or all the sections are sort of finalized in that way. But yeah, that's a super interesting question, and I wish I had a better answer.
No, I mean, again, as you say, it's early days, and adversarial attacks are pretty kind of niche field in any case. The one thing that made me wonder about that was just like, you imagine you embed the algorithm on the sensor essentially, and now I would imagine it's easier for people to physically get access to the algorithm, and then you get into extraction attacks, basically like replicating the algorithm so that you can figure out what its weaknesses are. Is that something that would generally be easier if because the algorithm is physically accessible down to downstream actors, or is there a reason that's not the case?
Yeah, so I mentioned before with the password example where you can take those hashes and you can run it through a hash table, and you can it's going to take you forever and whatever, but you could feasibly steal their passwords if you had the expertise and the time. And it's the same with this. If you really had the time and expertise, you could probably do something finicky with a sensor and screw with the internal structure of it. But I think it would be difficult, and there's probably ways of protecting against that. I know we were discussing. Also, you can also imagine someone, they take the memory and they try and flash like a new model on it, which would screw with the
Right.
With the model architecture, especially if it's like a cascade of effects, like maybe it controls your lighting, heating. So you could probably do some funky things with that. But yeah, so you could probably defend against that if you did certain things. Like, for example, I proposed that to these people that you could make it with ROM chips, so you can't put any new model on it. Obviously, there's limitations of that because you can't update the model either. So if you do find a problem with it, you're kind of just stuck with this broken model. But yeah, there's pros and cons. Like maybe the ROM way is the correct way, or maybe it's not. It's kind of hard to say at this point.
Actually, one thing I wonder is sort of like look at the future of this paradigm. Where do you see it being applied first? Like, are there some areas where you see low-hanging fruit where, like, okay, ML sensors would probably be a good fit for this use case?
Yeah, so I mean, we really think that the two main ones are going to be keyword spotting and person detection, and so that's kind of why we're making this open source person detection framework, just because it's not really like it's a very simple, easy to understand example, and there's plenty of things you could do with it. I've mentioned the like lighting and heating. You could link that to other systems, which maybe like count how many people are in a room, and maybe that could be useful for fire codes or predicting other aspects like that. So I think that would be the main ones. There's a lot of downstream things people could do with that if we released it open source. But one thing we were discussing is, there's downsides to this, and like if you have very niche applications, maybe it makes more sense for a company to make their own system as opposed to sort of an open source ecosystem. But then that leads to potentially problematic applications. You could imagine you could use this same technology in the same way that you could use TinyML in a negative way to target specific groups, for example, or ethnicities, things like, especially if you're putting this intelligent technology in things like bombs that only target specific types of people. And that's just, I don't want to say it's an inevitability, but that's just something with any technology, it can be used in negative applications. So obviously I hope no one does that, but it's possible. So
it's one of the challenges, actually. Like we often have this discussion with some of the folks I work with on the national security side, where you're looking at what can actually be done. We talk about weaponized drones, things like that, and it is frankly an inevitability, as you say. There's no incentive not to do these things. And so it's a question of like, how do we take the lead time that we have right now to look at these paradigms and say, what are the principles of design that we want to inculcate? What are the best practices? What are the ethical questions that are likely to come up in the future? And I think that's a big part of the reason why this work is so important, why it's so great that you're already putting your finger on this and sort of exploring the paradigm. So thanks so much for exploring it with us here today and for sharing your thoughts. This is a great third time around. By the way, I just want to ask, I know you guys have a website, right? mlsensors.org, is that it?
Yeah, that's kind of like our working group website, if you like.
Okay, great. So if people are interested in the concept, want to learn more about it, that's a great place to dig into it some more. And there's a great blog post as well that Matt published on Towards Data Science. So we'll share that here too. Is there anything else you wanted to share?
Yeah, so I'd say, this is kind of the brainchild of Pete Warden, who is one of the creators of TensorFlow Lite Micro, which is how you embed these models on sensor systems. And he also has several blog posts on this for people who are still like, what is an ML sensor, or why is this important even? And then we have, if people really want to get deep in the weeds, we have an archive paper, and we have a few other things coming out sort of later this year. And so I'll probably share those on social media if people are interested.
Awesome. So everybody stay tuned for that. And I'll share Matt's Twitter handle and a bunch of these links in the blog post that'll come with the podcast. Matt, thanks so much again.
Thanks, Jeremy.